We're recording, good. So thanks everybody for coming again, and it will be my pleasure to introduce Roger Smith. Roger's a engineer scientist at Caltech, and been an electrical engineer for astronomical cameras much of his career, all of his career. And right now, he's going to tell us a little bit about the upgrades that are being done to the 48-inch telescope on Mount Palomar, but also a little bit about surveying the sky much faster than has ever been done. So you've probably all seen his bio and the abstract on the talk, so I will not repeat that right now. I will just hand it right over to Roger. And thank you for coming very much tonight.
All right, well it's indeed an enormous pleasure. It's a pleasure to be here talking to you, but it's also a pleasure to be here. Here in this part of California, where there are just so many people doing so many interesting things. And so I'm actually going to spend about half this talk looking at an engineering project that we're doing now. We build one-off cameras for astronomy, so it's always something a little bit different, and I'll point to some of the technical challenges. I think there's so much talent in this room from talking to you that I'm going to be perhaps giving a talk that's for too general and not technical enough, so feel free to launch into any questions or anything about technical things, and I'll be happy to talk about that. But I'd like to also spend the first half of the talk actually telling you a little bit about a personal journey of my own, which is I have found very exciting and interesting from my own perspective, but also that it gives some sort of insight into how privileged we are to be in this area, and how privileged I am to be working on a project which has been funded to the level of $18 million by generous contributions from private and public institutions. And a very reasonable question is to ask, why would anybody spend $18 million building a camera to go on an astronomical telescope? We've got so many problems in the world, why would we spend our money like that? And I started off in my career being a little worried that I was just going into something to have fun and that I wasn't actually addressing these issues. And so my opinion on that's changed, and I hope I can convince you that it's rational. Anyway, the gist of the talk is to look at an engineering problem where we were asked to make something go 1,000 times faster. So this automobile was built when I was 5 years old, and it was considered a pretty nifty, speedy Italian sports car. And Volkswagen bought the name of the company, Bugatti, and they built the fastest street-legal car on the planet, which I believe does 430 kilometers an hour. It's been recorded at that. And unfortunately, though, that's only a factor of 2 faster than that original Bugatti over 70 years of development. And in that period of time, astronomy is going about 1,000 times faster. And so I'm going to show you today how we do that. But I want to point out that the rules of the game here are even more restrictive. You have to go 1,000 times faster in the original car. You're not actually allowed to build a new car in this particular game. We've got to use our original telescope and make it do better. Right, so before we get into that, where did I come from? Well, actually, quite literally, there. That was my high school, looking across Sydney Harbour in Australia at the Harbour Bridge, the Sydney Opera House, which you will recognise, and you'll also notice I'm an Australian from my funny accent. I'd like to point out that about a few years later, I graduated from high school in '73 and was doing a physics, undergraduate physics degree in '76. And that was when the Viking 1 lander took the first pictures of Mars. And I read an article about Viking 1, and I was stunned that they had built, in those days when we had 2D imaging television cameras, the cameras they put on Mars were made with an oscillating mirror and a photodiode, and they were encoding the radio signal synchronously with the tilting of the mirror, and they were doing the horizontal scanning by just rotating the towers. And so there are the 2 cameras. Now, that stuck in my mind. I actually had to go and find the article when I was preparing this talk, after 40 odd years. And it stuck in my mind because the experience of reading that article left me feeling devastated. There I was on the wrong side of the planet. All this stuff is happening and I'm out in the boonies in Australia, in a country which has very, very little research funding. How do you get from there to here? Well, the answer is incrementally. One of the things you do is you really can't see with this projector. You've got to start being a little curious. That helped. I was very enthusiastic about everything I did. I still am. This picture here has blurring over here on the left, and it's showing how the camera scans up and down because in fact they were photographing the ground just as they landed and the dust was floating around the place, and it takes time for the thing to scan from left to right, and so you can see the dust in the photo. So I was already thinking back then, gee, why did they do that? And that sort of worked well for me over the years. I didn't know anything about astronomy yet, but there was a piece of newspaper clipping about 3 centimetres by 2 centimetres on a notice board, literally this big, saying, you know, position available for summer students. And I needed a job, I didn't know what an observatory was, so I applied. And they liked me, I liked them, and a couple of years later, oh my gosh, I've faded out. There's a picture of me with my 1970s face in this control room with these guys. These turned out to be two fellows building the preeminent 2D imaging device of the era. I didn't know this. My boss just said, go up to the observatory and talk to these guys. They've got some equipment that I'd like you to look after. And so they sat me down, and in 3 days they went through books and books and books of circuit diagrams and explained this thing at lightning speed, got on the plane and left. And I had this 2D imaging photon counting system to look after, and well, there were a few bugs in it that didn't quite work, so I just didn't know what to do, so I started taking it apart in the lab and trying to figure out how it worked. It had a 4-stage magnetically focused imaging intensifier, and to focus the thing after you replace this component here, you have to put your face right up to the phosphor with a microscope and look at the spots and change the voltages until the thing comes into focus, while all of your hair is sticking to the high voltage cable and it's going zick, 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 zick in your ear. And the big benefit of moving from this to semiconductor devices, in my view, is that if you make a mistake with a system like this, it kills you. Whereas now, if you make a mistake, you kill the device, so it's much better. Anyway, that's in a museum now. And so, you know, we moved on. I'm going to just talk for a minute about the circumstances, but I want you to absorb this photograph, which was taken in the era of photography, still 1979, of the Anglo-Australian telescope, where I was working. And if you look at the lengths of the trails, you'll see that that exposure is about 11 hours long, and that the dome is still not overexposed. It's still very dark. But what I was going to tell you is that I also benefited from astronomical photography because there was a 19-year-old girl who showed up in the darkroom who was a student, and I realised that I had to ask her out pretty quickly because I was in an organisation full of males, and I did. The date went well, so I decided immediately I wanted to marry her, and a year later we were married. She was just 20, and we moved to the Cerro Tololo Observatory, operated by the US National Science Foundation in Chile, in the Atacama Desert in northern Chile, where we proceeded to have 3 children, though not immediately. I worked there for 18 years, and in the process became the resident expert in charge coupled devices, which I'm going to talk about later. Now, this image here, can somebody turn the lights right out? Is that possible?
Yeah.
Because we don't have enough contrast in this projector. I mean, we've got too much contrast. We don't have enough resolution. This image here is it's still pretty crappy. I'd like somebody to come and have a look at this on my screen at some point. Because you're supposed to go, oh, wow! This is an image of the Milky Way, the Large Magellanic Cloud and the Small Magellanic Cloud. This image took 20 seconds. it's essentially the same image as I showed you with those star trails a moment ago that took 11 hours. And this is sort of illustrating the improvement in sensitivity that we got between a silicon wafer absorbing the photons and a photographic emulsion absorbing the photons. This was, I think, the first picture that somebody had made with a scientific CCD behind a camera lens. This was a liquid nitrogen cooled camera, so it had very, very low dark current. And I could get, and it had quite decent readout noise, about 3 electrons of readout noise. So I could work in very, very low light conditions and make a nice high dynamic range image in only 20 seconds. And this was, of course, illustrative of the kind of thing that the astronomers needed. I immediately realized that, of course, I could not needing an 11-hour exposure and doing 20-second exposures, I could make movies just by taking sequences. And so on my way from Chile to Caltech, I took a little sojourn to the Mauna Kea observatories. This is the Keck 10-metre telescope here, looking almost straight at the moon, which is not something you normally do with a 10-metre telescope. And the image on the right is the Gemini 8-metre telescope. And in fact, I'd very much like to show some of you later some of these movies because they're quite pretty. They don't show up very well on the projector. What you'll see in a moment is the stars of the Milky Way going by in front of the slit up here. This is just illustrative of the fantastic sensitivity that we can achieve with these cameras. So, anyways, we're just working our way through to the present. Now what I do is I build, and so does Patrick. Patrick, hand up over there. Patrick works in my group. We build instruments for the Keck telescope, for Palomar, and also we're building new ones, much bigger ones, for the 30-metre diameter telescope that's under development. The headquarters are in Pasadena, just down the street. This is actually an offshoot from Caltech, this project. Okay, so that was how I got here. I got here incrementally. I went from one observatory to another, I met people, I saw opportunities, I just followed the next incremental step, and now I find myself working at a famous astronomy department, collaborating with people at JPL, doing some consulting work for space missions and building a very, very large camera for astronomy. So I'm going to take another detour now, quickly, hopefully, into why. I bet a lot of you here have had a lot of contact with astronomy, and this is somewhat redundant for me to tell you these things, but I started out thinking that it was rather a luxury to spend your time looking at these things, and I came to realize that astronomy actually provides us with the same or better insight into our place in the universe and our whole outlook, as do art, religion, geology, biology, evolution. How? Because they provide a bewildering sense of scale. They provide context for timescales, not just on human or biological timescales, or even geological, but beyond that, and a sense of the enormity of the universe. There's a fantastic laboratory for physics. Many of Einstein's impossible to verify predictions about things like curvature of the path of light by gravity, of course, have been led to gravitational weak lensing. We see just recently that gravity waves have been discovered. So, beyond that, astronomy tells us about how the elements from which we made came into existence. I'm sure many of you here have a gold wedding band or a filling, and those things can only be created in a supernova. So it sort of points to the fact that the Earth has been formed from the remnants of supernovae. So the history goes way back there. And ultimately, it challenges our preconceptions of who we are. And there have been some pretty serious run-ins with important institutions on planet Earth as a result of this, as you well know. It's incredible that astronomy can tell us the age not only of the Earth and the planets, but of the Milky Way and even the universe. When I started in my career, I would go to morning tea with the astronomers, and they'd be debating as to whether the age of the universe was 8 million years or 8 billion years or 18 billion. And now we've got multiple methods for determining the age, and we can pin it down to an accuracy of 100 million years, which is just incredible. Galaxies are only a recent discovery. And this is actually kind of scary, this sequence of pictures I'm going to tell you. So we start with Messier, who was a comet hunter, and he kept on finding smudges in the sky that looked like comets, and they were kind of annoying because they didn't move around the place, and therefore they weren't comets. And so he made a catalogue of things to ignore, and he became the famous discoverer of galaxies. He actually didn't have good enough optics. He was using basically crude eyeglass optics. They made, lens makers for eyeglasses, as you know, were the first to build the components of refractive telescopes. And so, there's an assortment of globulous clusters, clusters of stars, clouds of gas, galaxies of different morphologies, supernova remnants, supernova remnant over there, hydrogen emission, all sorts of things. He didn't know what it was. But, to give him a bit of credit, in 1920 we still did not know that the universe was larger than the Milky Way, and there was an enormous debate about whether or not these structures here, these cloudy things, these nebulae they would call them, were inside the Milky Way or outside the Milky Way. Well, it turned out that two women working at Yale, who were scanning photographic plates at the time mostly, determined that there were a class of variable stars whose pulsation period was related to their brightness. And so you could observe the pulsation period, and then you could say, well, I know its intrinsic brightness, and therefore I can measure its observable brightness, and then determine from the R-squared law how far away it is. Now, you might wonder, how do you know how far away they were in the first place? And the answer is, you look and find a whole bunch of them in the Magellanic Cloud. You know they're all the same distance away because they're in the Magellanic Cloud, right? And so you use that to calibrate the system, and then you apply it to other galaxies. It turns out they didn't think to apply it to the other galaxies. It was Edwin Hubble who did that, and he resolved the issue by showing that these galaxies down here were actually so far outside the Milky Way that it was impossible that they be inside, and at that point the universe expanded just by the mere act of realising that all these things were actually beyond, and so now we have multiple galaxies, and the whole concept of a galaxy was born in only 1925, when my father was born. Hubble went on to put together some with another guy called Humason, also at Caltech, by the way, both of them at Caltech. You never hear about Humason anymore, but they related the distance to the velocity, and the velocity measurements they didn't even do themselves either. That was done by a guy called Sulfur at Lowell Observatory in Flagstaff, but they put it all together and realised that the universe was inflating and expanding. Everything's moving away from everything else, like raisins in cookie dough or dots drawn on the surface of a balloon that you're inflating. So this set the pathway for cosmology, and of course today we now have a telescope named after Hubble, and it's in space, which is great, and we don't have any trouble at all telling what's a cloud of gas versus a galaxy. There's some gas clouds. In fact, this one's great because you've got the remnant of it's not a supernova, I don't think, this thing. I think it's some star shed its shell and blew this bubble, but it's embedded in a big cloud of hydrogen, which is pretty cool. Andromeda Galaxy, the largest of the nearby galaxies. It's pretty impressive. You can actually see all of the dust lanes extincting the starlight and the clouds of hydrogen here in Andromeda, and so forth. Astronomy, though, this perspective thing I'm talking about goes further. Back pretty recently, people started to look in the holes beyond and between the galaxies that we were observing And so they started to look beyond the Milky Way. This is a mosaic of images made by the Pan-STARRS project of the Milky Way, the dust lines, but people started to look out in these spaces far away from the plane of the galaxy to see what they saw, and of course Hubble showed them that there were lots of galaxies, interacting galaxies, clusters of galaxies whose mass are bending the light and tearing the light apart, making these arcs here and here, and that light came from the same source. And that's the bending of light by gravity that's done that. There's a little diagram up here showing how all that works. You know, the light goes around the mass and curves in, and you see it coming from two different directions. You know it's the same source because it has identical spectrum, and nothing else in the picture has the same spectrum. And you keep going and you find out that there are all these elongated arcs all over the place. This is another cluster of galaxies, and then people realised that they could deduce how much matter is there, and you can see the dark matter, measure it I mean, by looking at the bending of the light. And that's pretty cool. But there was a guy I used to go jogging with. He happened to be our observatory director, about 15, 20 years older than me. He would always run further and faster. A very determined fellow, and so when he became director of the Space Science Telescope Institute, which runs the Hubble telescope, he decided that he would take all of his director's discretionary time and put it into one image. And they went orbit after orbit after orbit and co-added the images to see what you would see if you looked further into the distance beyond and between all of the things that we could currently observe. And what they saw was this, the Hubble Deep Field, and there are only a couple of stars in this image, and you can tell the stars because they're bright enough to see their diffraction spikes, and they're of course point sources. You can tell by careful measurements, the PSF, that they're point sources. But all these dots, even these very faint dots, they're galaxies. Everything in here is a galaxy pretty much. And so people got quite pretty excited about this, and discovered that it's sort of galaxies everywhere we look, and this is zooming back, bigger and bigger picture, looks just like the other picture, it doesn't matter where you point, you see galaxies. So we can estimate how many galaxies over the whole sky, and the answer is there are as many galaxies as there are stars in the Milky Way. That's a lot of stars. How many have planets? What about the odds that life came into existence by accident? Well, this how many have planets question is sort of pertinent to that, isn't it? Because if you counted how many stars there are, and then you know whether a large fraction of them have planets, you have kind of a fairly large number of times you throw the dice. So what's this planet story? You know, goes back a ways, of course. I found it interesting, though, that astronomy was having an impact 2,500 years ago when Aristarchus came up with the current model of the solar system. And it was rejected on the bounds of impiety. He was rocking the boat too much, people didn't like that. And the same thing happened to Galileo, of course. He had a bit of a run-in with the Pope over his observation that the moons of Jupiter were orbiting Jupiter and not Earth, and that, Moon was orbiting Earth, but there were moons around Jupiter. But he had a tool, he had a telescope that Aristarchus didn't have, and it's optics. It's the Optical Society, right? It's optics that came into play and made all the difference because other people could make the same observations, and so science was underway. Finding truth through observation by allowing people to confirm or deny your hypothesis and decide whether they believe you. Zooming forwards now to the Kepler mission, which I was involved in, they decided they'd try and answer this question about how many planets, and so they made a very nice focal plane which consists of a whole lot of charge-coupled devices. These are silicon sensors. They're on the chords of the sphere because they're using a Schmidt telescope which presents a spherical focal surface, and there are field flattening lenses individually on every CCD to deal with the deviation between the flat image sensor and the curved focal surface. You're going to see that configuration later in our instrument. they pointed this at the same piece of sky for 4 years, and you can see on my screen, you need a better projector, that there are about 1 million stars in here. And what they did was they watched those stars for 4 years continuously, measuring them every 2 or 3 seconds, and they co-added all of the data, and they got extremely high signal-to-noise, and they were able to detect attenuation in those stars down at the 50 to 100 part per million level, because they just kept on integrating and averaging and averaging and averaging, so the precision kept going up. As the telescope pointing dithered around due to vibrations in the spacecraft, which always exist, they developed a correlation function between the pointing of the telescope, which was very easy to, very precisely derived by using all those stars to see where the telescope was pointing, and then they could determine the change in the photometry as a function of pointing, decorrelate the data so that they would remove that error, and then look at the residuals. And so they could tell very, very accurately how bright all those stars were. Now, some of the stars have intrinsic brightness fluctuations because of changes in the stellar atmosphere, but the majority of them were chosen because they are stellar types that have very stable flux. And then as planets would orbit them, they would pass in front of the star, and the planetary transit would reduce the intensity of the star by a few hundred parts per million. The period of that attenuation, those transits, would tell them what the radius of the orbit is. The depth of the transit would tell them in relation to the assumed, they could look at the brightness and the class of the star and make an estimate for the stellar diameter, so they could actually get an estimate of the diameter of the planets. They could look at the shape of the edges. There's a lot of data there. So they made a histogram of how heavy planets are, how far they are from their stars, and for that matter, how many stars have planets. And so there's lots of data, and you could go forward and figure out how many of them are in the Goldilocks zone, not too hot, not too cold, rocky planet, right gravity range, are they Earth-like? So let's just take that number, that 18 there, of sort of Earth-like planets as a fraction of all of the planets that they found, and know that they concluded that most stars have at least one planet, and many have multiple planets, and you're up to about 10 to 19 planets in the habitable zone. 10 billion trillion Earth-like planets. So, I'm feeling like I'm an accident. I'm feeling like I came into existence by accident at this point. There's an awful lot of chances for life to exist. So, these are just my examples of ways in which astronomy can have a profound effect on our perception of who we are, what we believe in, where we fit in. If you're interested in history for these reasons, well, you should be interested in this sort of thing too. So back on my planet, back at ground level, I'll now talk about my project. So this guy Fritz Zwicky was an astronomer at Caltech who in fact founded the field of astronomy, which we now call transient science. Yeah, pretty amazing career. He was the one who discovered and described neutron stars for the first time. Supernovae. He held the record for the most supernovae detected by a single person until very, very recently, even with his limited instrumentation. He was the discoverer of dark matter, the fact that 90% of the universe is dark and not detectable. He also posited gravitational weak lensing. He received a presidential award for rocketry during the Second World War, and he had 50 jet engine patents. Busy guy. Meanwhile, Hubble over here, the poser who got his name on the telescope, he only discovered that there are galaxies beyond the Milky Way and the expanding universe thing. What I find interesting, of course, is that I get to climb around inside his Hubble. I get to climb around inside Hubble's telescope, building instruments and putting them in there. And we've already put a